Hi. So now what we'll do is very interesting, is the equation that we finally got, right, using the similarity variable. Now that we're going to solve, it's a, like we just said, that it's a third order ODE, right? And we have just one equation to solve, and we will solve one equation and we will get a picture of the u and v velocities across a boundary layer. Okay, so that is essentially the purpose. And okay, now, so basically let me show you first let me show you that what the outcome of solving this is, and then I will talk a little bit in detail about how we go about doing that, developing this little piece of code. Right now, this is something that I will post. Okay, I will post. It is also this is also available freely over the net, I think, and if you feel free to use all that information. Okay. To do this, you will need a little bit of practice, or a little bit of understanding of how one does coding. Okay, you can do this in whatever form you are comfortable. I have done this using Scilab, like I said to you. So this is my Scilab console, as you can see. Okay, and I'm going to use this to basically run the code that I have written. So before I explain the code as to how we go about that, and a numerical method which we've used to do this, let me first sort of run this and show you that what is the output, right? And what do we mean by that? So basically I take that equation and I use a little computer code to solve it. Okay, and what is the outcome of that? So what I'm going to do is just, so this is how this is how the code looks like. Okay, I'll explain that to you a little bit. So what we use is a fourth order Runge-Kutta method. Okay, I'll come to that in a bit. Okay, so and then we get essentially the output. Okay, so as you can see that I have an output, right, of eta. Okay, and several other things. So let us see, and then we also plot. So let me show you what the plot means. So all I have to do here, okay, so I'll talk briefly about Scilab also. Okay, so this is my output. Okay, now let us see. Now the first things which you will be a little familiar with is this one. So what we get from the plot, right, what we get as an output from this plot is this value called y2, right? y2 comes from the code, right? So what I'm able to plot out, if you look here in this y-axis here, is f dash, right? And from what we developed so far, f dash is nothing but u by u infinity. Right? You remember u is equal to u infinity into f dash, right? So in the solution here, so what I have done is plotted basically f dash, right? F dash and the in the vertical axis, and eta at the on the horizontal axis. So what I've plotted is how u by u infinity varies as eta, right? So basically you can say this is a plot of f dash versus eta, right? It's just that u by u infinity is what is f dash, right? So this is the variation of u by u infinity or f dash with eta, right? So this is this plot that we get. And what is important to understand here is that I don't have to calculate anything. I get f dash as a direct output of the solution, right? The numerical code that I write, it will give me directly f dash. Okay. Okay, so this is one of the plots. Let's see what else we have. We also have this plot. Okay, So we can plot a lot of things. So I have this, I have also plotted f, right. So what is f? F was the non-dimensional string function, right. So we've got f as a function of eta, right. So this is again something that you get. Then, so that's one of the plots. Look at this. So we get y3, which is nothing but f double dash. So we also plot f double dash versus eta. So essentially what we're doing is, so this is f dash, okay. So this is f. So this, in the window 1, if you can see. So this is window 1, okay. At the top you can see window 1. So this is f versus eta, right. Then this window is basically showing you, let's see if I can do this at the same time. Okay, and so this window shows you f versus eta. This shows you, window 2 shows you f dash versus eta, right? And then this window shows you f double dash versus eta, right? And what is important to understand here, that these are basically direct output from the code that we write. Okay, so so having done that, okay, let's sort of minimize those. Then look at this, okay. So if I plot this, all together, okay. So we have sort of several plots here. So I've plotted basically all of them together, okay. We've got the pink one is essentially the u velocity, okay. Then the green is v velocity, okay, and there are basically the blues. So one is this y1 and the other is y3, okay. So y1 I think is f, right. So y1 is, y1 is f and y3 is f triple dash, okay. So we get that. And if you look at this one, so what we get here, if you see now, right, so we get this term here, u by u infinity, right, under root of x u infinity by nu, right, is equal to half of eta f dash minus f, right. So this is your eta, right, this is your eta. So now the interesting thing is that, so this is what we get as a result of the, as an output from the code, right. Now, what you should pay attention to here is that, for example, because this is the plot that you would be really interested in. Now, what you should understand here is that eta is a similarity variable. Now, eta itself, right, has x and y in it, right. Eta itself has x and y in it, right. Now, if you see this plot here, okay, if you see this plot here, for example, say for a eta value of 5, right, the value of f dash is 1, okay. For eta value of 6, the value of f dash is 1, okay. When will value of f dash be 1? So now what I'm beginning to do is kind of read, the plot. I think that's very important. Read the plot, okay. Otherwise, these are just a set of lines, okay, or some markers. I mean, they need to mean something physically. Then they'll, then that's the purpose of writing all this code. Now, so at eta is equal to 6, again, f dash is 1. What does f dash 1 mean? That u is equal to u infinity, meaning that u is equal to the free stream, right? Now, what is interesting is that eta, right? What is the value? How do we write eta? So, eta is a function of both x and y. Remember, it is y under root of u infinity by 2 nu x, right? Now, if eta is equal to 5, right? So, what does that mean? What does that mean? Now, take a certain value of that x, right? If you take a certain value of x, right, then you will get the value of eta is 5, right? The value of eta is 5. What should be the corresponding value of y? Right? You know that for eta is equal to 5, the f dash is equal to 1, right? So, what I am saying is in the eta there you have a x and you have a y, okay? Now, you know the value of eta, which is 5, so put that as 5, okay? And you got x and y, so I am saying fix x, right? Fix x, so let x be 1, value of x be 1. Right? Then what should be the value of y to get an eta of 5, right? Similarly, change x to 6, right? And eta is 6, right? And change x to say another value, then f dash is still 1, right? The corresponding f dash is still 1, right? So, find out the value of y. Right. So, that is very interesting, and now that should give you a feel for the velocity profile, okay, across the boundary layer, which is what we were doing. So, basically all these plots that we wrote out, etc. Now, you should be able to get all of that, okay, from this. Okay. Now, I will elaborate on that a little bit more, that what do you get out of this, okay, how do you sort of represent this and so on and so forth, okay. Now, let me come back to the code a little bit, okay. Let me sort of give you a little overview of how we sort of do that, okay. So, what I essentially did here is, this take several values of eta, okay, I have written here. So, I take a start value of eta to be 0 and eta, the end value is 10. Okay, and we take the y3, which is f triple dash. So, these are kind of like boundary conditions, you might say. Okay, so we are going to take this as in this particular code I have written this. So, f double dash is basically the second derivative at the wall, okay, which is the initial assumed value, and we call that as y3 wall, which we take as 0.5. This is an initial assumed value, as you can see. Then first derivative at eta. So, now f dash, right. Now, this is our boundary condition which we are using, right. So, first derivative at eta is equal to infinity, right. At eta is equal to infinity, f dash was supposed to be 1. Right. So, we have got that. So, that is the expected value. So, that is all basically we know, and at the wall u is 0 and v is 0. Okay. So, eta values, so start values of eta, and so when I say here for example evaluate delta eta, so I take small, so I go from 0 to 10, right, I go from 0 to 10 in steps. So, I divide that entire range 0 to 10 into 100, right. So, I go from 0 to 10 in steps of 10 by 100 basically, right. So, those are little steps. Okay. Now, the Runge-Kutta method is essentially it's a method of integration, numerical integration, that when we go from one set of boundary here to the other. So, here physically this also means that I am going, I am kind of, in this particular case, all I know is that what I know here is that the y2, right? So, the y2 or at the wall, right, at the wall sorry, at the free stream or at the edge of the boundary layer is going to be 1 or infinity, whatever we have written here, f star, right. I know that value. So, here what we are basically doing is that I know that value and I am going to come and so that is a value I know. So, I kind of start from that value. You know, y3 is again something that you know, I am not aware of. Okay. So, I use that, right, and I kind of go from the known value, you know, to the other end. Right. Now, here what we are basically doing is we will go from the wall, right, up to the, so the wall value is something that I do not know. So, I assume it, right, I assume it. Now, once I assume that, I use that value and I integrate forward away from the wall into the boundary layer and I go to the edge. Now, there I know one value, which is the y2 value there. So, that is a value that I know, right. But do I reach that value with the assumed value of y3 which I started? Not really. Okay. So, what I need to do is go and come back, you know, and do this again with a different starting value at the wall, right. So, therefore, this is an iterative integration procedure, right. We do that and that is exactly what we will go ahead and do that. So, in this particular case, and also we take, you know, several values of eta. So, Runge-Kutta is, you know, so that is how we go about basically implementing the Runge-Kutta method. Okay. So, this is again, you know, it is a very standard method. This is a standard method and I think that well, I think you can sort of see that here, for example. Now, we start out here, for example. So, I say ky1, okay. So, it is a fourth order Runge-Kutta, right. So, I basically, when I go from one eta to the other, right, one eta to the other, I take two more points in the middle. I take the two edge points, right, the start point, the end point, right, and I also take two more points in the middle. So, that is why it is a fourth order Runge-Kutta. You could have a second order or third order as well. Okay. So, now therefore, what I do here, right. So, first is I write, you know, this is a value that I write. I mean, I am using this variable ky1, okay, y2, right. ky1 is y2, okay. So, these are values. So, now y2 first derivative of f, right. These are the boundary conditions. So, the first derivative of f which is at y is equal to 0, right, f dash is equal to 0. So, f dash is what I am calling as y2, right. So, right. So, ky1, okay, ky1 is equal to y2, okay, then ky2 is equal to y3, okay, and this ky3, right, I am writing here, as you can see, is minus y1 and to y3. So, basically these two values. Now, this is where I implement the equation, which is f triple dash, I mean the equation that we are integrating, right. In this particular case, our our boundary layer equation using a similarity variable. So, this actually comes from there, right. So, basically I am looking at f dash. So, I get this from there, right. And then again, this is something which is the method. When I come to the second point here, this is something which is essentially the part of the Runge-Kutta solution. Okay. So, Runge-Kutta solution, and so what I am doing is that I do this, right, and you can see ky1. To that I have the original y2, right. To that what I do is I add this. I add half, right, delta eta, okay, ky2 1. So, this ky2 1 which comes from this step above here, right. Again ky2, so this is y3 which I had previously. To that again I add half into delta eta, right. Delta eta is the the space in which I am carrying out the integration, right. So, into ky3 1 which comes from here, right, and here ky3 2, right. So, 2, so then it goes from minus y1 y plus, okay, 0.5 delta eta ky. So, again, so this here, right. So, I got y1 and y3. So, right. So, here what I get is, so I change both basically, with delta. So, I say y1 plus 0.5 delta eta ky1 1, right, into y3 plus 0.5 delta eta ky3 1, right. So, these are the essentially the 2 points. So, this is something, and then once I get this, right, I again come to this point where I say ky1 3, which is nothing but y2 plus 0.5 delta eta, right, ky2 2. So, ky2 2 is which I get from here, right, which I get from the previous step. So, ky2 2, then ky2 3 is y3 plus 0.5 delta eta ky3 2, and ky3 3 is simply y1 plus 0.5 delta eta ky1 2, right, plus y3 is ky2. Okay. And finally, we basically take the the fourth point, which is ky1, okay, y2, and so on and so forth. Okay. So, then basically what we do is calculate the function values at the next location, right. So, what I am saying is we take the surface, let us say this is my surface, right. So, I start from here and this is my edge of the boundary layer. So, when I go from here to here, right, so I will not go here like directly. So, I am going to go in steps. So, in this case I have taken 100 small divisions, right. So, what I just showed you 1, 2, 3, 4 is that when I take a small little division here, right. So, in this division I am integrating my function, right, which is what? So, basically the equation that we have derived using the similarity variable, I take that and I solve it in this little distance from the wall. So, little that is my domain, you can say that. So, go from here to here and I take 4 points there. One is at the lowest boundary, one is the toppest boundary, and 2 in the middle, right, and hence it becomes a fourth order Runge-Kutta method. So, you go from here to there and then you go in, so once you, so therefore you find out the edge and again go to the next step, right. So, again go to the next little gap and then so on and so forth till you reach the edge of the boundary layer. So, that is what we basically this code is doing, right. So, so then this is again, this is part of the boundary, the Runge-Kutta solution. So, when I calculate the function values at the next location. So, all I do is, so I take y1. So, basically what y1 here is, y1 is f dash, right, y2 is f double dash, y1 is essentially f, right, y2 is f dash and y3 is f double dash. So, that is what these things mean. So, y1 at I plus 1, what is I? So, if you take I, say this is your surface. So, I is basically an index, right. So, I go from here, so the next step, so I go to the next little step, I go to the next little step and so on and so forth. So, I call this 1, 2, 3, 4, 5, right. So, what I am calculating is, so I went from the boundary, surface boundary, and I go to the next one. So, when I go to the end of this little step here, right. So, basically what I am doing is I am solving this discretely, right. So, then I write I plus 1, right. So then I, and 1/6 of delta eta, and all these values that we've calculated at the 4 points. So, okay, y1, 1, 2, 3, 4, right. Similarly for y2, so I do the same, and for y3 we do the same, right. And then all I have done is, so once you do that, so basically what you have now is value of, so therefore as you go up, at a certain location, as you go up you have the values of f, f dash and f double dash. This is something you have by solution of that equation, right. Now how does that help you? The reason it helps me is because my horizontal component of velocity, right, let me see if I have that here, right, because if I know f dash, right, if I know f dash, f dash, it basically means I know the value of velocity u, because f dash is nothing but u by u infinity, right. Therefore, this does give me a value of the velocity. So, if you see this is eta, right. So, like I said, from whatever I can see here, that from around say, from around say 3.5, or to be more safe, say for example from eta is equal to 4, right, f dash is 1. So, f dash is 1 meaning that it is free stream, right. So, if it is free stream, so that means, well, we kind of reached out near the edge of the boundary layer, right, near the edge of the boundary layer. So, this could actually mean edge of the boundary layer. Now, what this doesn't, this plot, what it doesn't, because now this is in the, in terms of the similarity variable, but what is it now? The next question for me, for example, what I would like to see is the picture that we drew of the boundary layer, right. So, where we have a velocity profile at several x sections. Now, how do I get that from here? So, that is what I said. So, there what you can basically do, you know the value of eta, right, and you know the value of f dash, right, which in turn means that you also know the value of u, right, and you can also calculate value of v, right, you can also do that. So, you got f. So, v is a little more of a complicated sort of an equation, but this is what it was, right. So, this is what this right hand side, if you see right hand side equation here is half under root of half into eta f dash minus f. This was the expression for v, right. This is the expression for v, and right. So, we get this, and this kind of boils down to something like this u by infinity into x u infinity by nu, right. So, and this is my eta at the horizontal axis. So, now that is what I said. So, now from this to draw your inference, for example, let us go back to this plot. So, draw your inference, all you have to do is take the values of eta from here, the corresponding values of f dash from here, and plot it for different x and y locations, right. So, that is something you should be able to get from here, right. So, now essentially eta is equal to y, right, under root of u infinity by 2 nu x, right. Now eta value is 5, that is not going to change, right, and I am also going to fix the value of x, which is 1, right. If I do that, what should be the value of y? You should be able to find out, right. So, similarly, if I then change x, right, there is a unique solution for y, for the same eta, right. So, that is something that you need to, or for example, you fix y and you keep changing x, right, then for the same eta, then what do you get? So, I think that's how you should be able to then, that information is basically going to be available from this plot. So, essentially then it will give you, the kind of velocity profiles you are used to seeing in terms of a boundary layer. So that is essentially, what we get from, for example, this kind of a plot. Now let me see, this is, yeah, so I guess, right. So now let me see if this is something different which I could show you, or it's one and the same thing. Okay, yeah, actually it's not much different. So that is probably going to be another, a part of your assignment actually. So yeah, so it's probably going to be a part of your assignment, where, okay, I can actually sort of talk about that a little bit. Okay, I can actually, yeah, so this is, this is probably going to be a little bit of a problem which I will pose for you when you do this. Okay, so one thing is, so let me just mention here that one thing is that you learn to code and things like that, but this is not a coding class, right? And this coding is not too exhaustive either. It's simple. It's nothing too complicated, and the syntax that you see here is essentially for Scilab. Okay, so this is the type of stuff that one will use for Scilab. So this is nothing too exhaustive. So what I will be expecting from you is not to really become a very great coder or anything, which you should do if you are interested. I mean, of course, you should do that. But what I will be interested to see, whether once when you get the plots, once when you the moment you are able to see a plot, like this, we did all the equations and then we are able to plot all this or get results like this, then are you able to interpret? Are you able to interpret the the various parameters of the boundary layer? I think that is more important, whether you are able to understand physics from these graphs. That will be my focus. Okay. So I think I will not go ahead and give you further information about Runge-Kutta method and all that. That is really for another class. So this is a code that I will post for you. I don't think that's a problem. You can run this in Scilab, and you can also develop your own using MATLAB or any other software that you're comfortable with. Okay, so if you are able to code well, wonderful. If not, it's okay, because what I will be doing here is giving you these plots. Okay, I will give you these plots and then ask you to do exactly what I just said. Then like draw a velocity profile, right, based on this kind of an information, right? So that you are able to interpret. Okay, so because ultimately the reason we did all of these things is to be able to solve numerically for the velocity profile, isn't it? So I think that is what is important. Okay, so I think we'll stop here and take this up for next time. So I think next time what we're going to do is, now we've just dealt with a flat plate, and next thing is, do we do only flat plates or what else? Not really. We don't do just flat plates. There are other things as well, but a flat plate is a good place to start. So I think that's why we did that. Things can get a little more complicated, right? So that's what. So fine. I will stop here, and we'll pick this up again in the next modules. So thank you.